Welcome back to Astronomy. This is Chapter 5, Light and Matter, reading messages from the cosmos. In the previous two videos, you learned about light and the properties of light, and we're going to continue on in Chapter 5 looking at the structure of matter. We're going to look at atoms and molecules and then how light and matter relate to each other. But we're going to take a little side trip here in this part 3 video and look at scientific notation. So it's not particularly about light or matter, but rather just how we write very large and very small numbers mathematically in a nice, concise way. So scientific notation. Scientific notation is a short way of writing large numbers, such as we have the number here, 50,000. And you could write that by writing a 5 with 4 zeros after it. But a concise way of writing it is to write the 5, and then instead of actually writing the 4 zeros, you just effectively say it's 5, and then with 4 zeros after it. So the way we say the and then 4 zeros after it, it's times 10 to the 4th. Now, 10 to the 4th power is actually 10,000. It's a 1 with 4 zeros. So we're multiplying 5 times 10,000 to get 50,000. Now, this becomes very important when you have very, very large numbers, as we often do in astronomy, such as this number, 6 times 10 to the 24th. So you could write that out, as I have on the right, with a 6 and then followed by 24 zeros. But that is a pain to write all those zeros, and it's a pain to read all those zeros, and there's a chance that either the writer is going to mess up on the number of zeros or the reader is going to mess up in interpreting. But it'd be easier if we could just say that our quantity is a 6 followed by 24 zeros. So the way we do that is, as you see on the left, scientific notation, 6 times 10 to the 24th power. So that 10 to the 24th power is a 1 with 24 zeros after it. It's actually 1 trillion trillion. So 6 times 10 to the 24th, when you see that, you should read it as a 6 and then followed by 24 zeros. And that, by the way, is the mass of the Earth in kilograms, 6 trillion trillion kilograms. We can take an even larger number, 2 times 10 to the 30th. And so the 10 to the 30th tells us the order of magnitude, how big it is, and the 2 really doesn't matter as much as the 10 to the 30th, so a 2 with 30 zeros after it. And that, by the way, is the mass of the sun. Now, if we want to think about the mass of the Earth versus the mass of the sun, if we didn't have scientific notation, we could write out the 6 with the 24 zeros and the 2 with the 30 zeros, and then we'd have to count how many zeros there are, and we would eventually come out with, after counting the zeros, to see that the mass of the sun is bigger than the mass of the Earth. But it's much easier to look at these numbers in scientific notation. The mass of the sun, I'm going to ignore the 2 for a minute because that's not as important as the order of magnitude, 10 to the 30th kilograms. The mass of the Earth, I'm just going to ignore the 6 for a minute, 10 to the 24th kilograms. So I can see right there are 6 orders of magnitude difference, meaning very approximately the sun being 10 to the 30th and the Earth being 10 to the 24th, the sun is about 1,000,000 times more massive than the Earth. Now we can get more precise with our numbering. Here's the first example I gave you. 5 times 10 to the 4th means 5 with 4 zeros after it. But what if I want to have a quantity that's a little bit more than that? Not as much as 6 times 10 to the 4th, but somewhere in between 5 times 10 to the 4th and 6 times 10 to the 4th, or 50,000 and 60,000. Well, let's look at this. 5.27 times 10 to the 4th. It still means that there are 4 places after the 5. Now notice I changed the way I said it. In previous slides I said 4 zeros after the 5. Well, they're not all going to be zeros. In this case, they are places or decimal places. So the first one is a 2, the next one is a 7, and then the rest of them are going to be zeros. So 5.27 times 10 to the 4th is 52,700. So we can think it's a 5, and then there are going to be 4, not zeros, but 4 places after that 5. It's just that the first place is filled by a 2 and the second is filled by a 7. Now we can get more precise. Let's increase our number by just a bit. Instead of 52,700, let's have 52,740. And so it's going to be 5 point something times 10 to the fourth, just as it was in the middle of the page. And that something that comes after the point is 274. So both of these numbers, the 5.27 times 10 to the fourth and the 5.274 times 10 to the fourth, are just a little bit more than 5 times 10 to the fourth. You have seen in previous videos the speed of light, and I've said that's about 3 times 10 to the 8th meters per second. And I explained it in the video that 3 times 10 to the 8th, that means 3 with 8 zeros, so 300 million meters per second. And that is an approximation. If I want to get it more precise, I can say that the speed of light is actually 3.00 times 10 to the 8th meters per second. Now that still means that there are 8 places after the 3, after that decimal point. It's just that the first place happens to be a 0 and the second place happens to be a 0. And so it's still the same. It's 300 million meters per second. I've underlined the 0 here to show that it's approximate, or it's precise to this decimal place. So it's 3, and then the next place is definitely a 0, the next place is definitely a 0, and then it's rounded off after that. So these are more just placeholders. Now, if I want to get very specific about the speed of light, if I want to get it precise to many, many decimal places, in fact, if I want to write it to its exact definition, I would write it like this. Now, the speed of light is actually, we say 300 million, but precisely it's 299,792,458 meters per second. If I wanted to write that in scientific notation, I would write it as 2, and then keep in mind there are going to be 8 decimal places after that 2, and they are filled by, so it's what comes after the decimal point, 997,92458. Now, this isn't really a more concise way. In fact, it's less concise than writing it out in standard notation, but this is the speed of light in scientific notation. If you compare it with what I've written in the top line, it's something, they're both something times 10 to the 8th. The top line is 3 times 10 to the 8th. And notice that the bottom line is just a little bit less than 3. It's 2.99792,458. But this is the exact definition of the speed of light as written in scientific notation. Earlier in this video, I said that the mass of the Earth is 6 times 10 to the 24th kilograms, and that can be written as 6 with 24 zeros after it. But if we want to be a bit more precise, it's a little less than that. It's actually 5 and then 9, 7, and 22 zeros after that. And so we can write that as 5.97 times 10 to the 24th. And notice if we ignore the times 10 to the 24th, it's just a little bit less than 6. It's 5.97. So scientific notation, when we think about the power of 10 that we're multiplying by, the power of 10 refers to the number of zeros before the decimal point. So let's look at this list. 5 times 10 to the fourth means 50,000. 5 times 10 to the third is 5,000. And you can see the list goes down. 5 times 10 to the first is just 50. And you can see it's more concise just to write 50. However, there it is in scientific notation. Now, what happens when we get down to the 0th power? Well, you look at the pattern on the right-hand column, and as we reduce the exponent by 1, we chop away a 0. So 4 zeros, 3 zeros, 2 zeros, 1 0. 5 times 10 to the 0th means it's a 5 with 0 zeros after it. So that just means 5. Now, perhaps you learned from math class that anything to the 0th power is 1. So 5 times 10 to the 0th is 5 times 1, which is 5. Now there's no more zeros to take away. But what happens if we reduce the exponent by 1? 5 times 10 to the negative 1. Well, 10 to the negative 1 is 1/10. It's like a dime as compared to a dollar. It's a tenth. So we're looking at 5/10. And there you can see it's 0.5. Now, we don't have any more zeros to chop away from the right, but what we're going to do is we're going to add them to the left. And so 5 times 10 to the negative 1 is 0.5. 5 times 10 to the negative 2 means 5 times 100th. It's like a penny compared to a dollar. So it's 0.05. 5 times 10 to the negative 3 is 5 thousandths, or 0.005. When I introduced this slide, I said, or earlier in this video, I said you can think of the exponent as how many zeros come after the main number. So for example, times 10 to the fourth means you put 4 zeros after it. When you go into negative exponents, now you're looking at small numbers. And you can think of it as the number of zeros. So the exponent, such as this times 10 to the negative 3, think of it as how many zeros there are before the 5, but you have to remember to count the ones place. So in this case, we have 1, 2, 3, and then we have the 5. 5 times 10 to the negative 4 is 0.0005. Notice there are 4 zeros before we get to the 5. So the larger the negative exponent, the smaller the number is getting. In astronomy class, we will tend to see these large exponents, these very large numbers, when we're talking about the masses, the sizes. Later we'll talk about the power that's emitted by a star. So the sizes and masses and quantities that involve things that are out in space. We will tend to see these small, these negative exponents when we talk about matter, so atoms and molecules and very, very small things. Now let's think about the electromagnetic spectrum. You've seen this chart before. Hopefully you have memorized the order of the electromagnetic spectrum by now. And if you haven't, you better get on it. But let's look at these numbers right here. The wavelength. Remember, gamma rays on the left of the chart are short wavelength. Radio is long wavelength. Let's look at these numbers now. 10 to the negative 12 meters. That means 1 trillionth of a meter. And as we move to the right, we get to longer wavelengths. So 10 to the negative 10, 10 to the negative 8. We're in the realm of very small numbers. 10 to the negative 6 is 1 millionth of a meter, or 1 micrometer. But as we move from left to right on the chart, we're getting larger and larger. So the size of a bacterium. Right here, notice it's 10 to the negative 4. And they didn't write it out. The illustrator didn't want to have too much clutter, but that would be 10 to the negative 3, so that's a millimeter. 10 to the negative 2, 10 to the negative 1, that's a decimeter. And here we have 1 meter. And they could have just written that as 10 to the 0th, but it's easier to write 1. Then 10 to the 1st, 10 to the 2nd. Now we're looking at 100 meters, and that's the length of a football field. It would go to 10 to the 3rd, that's a kilometer. If you look at the frequency, starting at gamma rays on the left, higher frequency, so 10 to the 20th, that's 10 to the 20th waves passing a given point per second, and then 10 to the 19th, 10 to the 18th, and you can see it goes down 10 to the 14th, a little bit more than 10 to the 14th is visible light. So notice visible light, let me bring it right on down through the bacterium there. It's a bit more than 10 to the 14th, right where my marker is, but less than 10 to the 15th. And so that's the frequency of visible light, somewhere in the 10 to the 14th to 10 to the 15th range. And it gets lower and lower, 10 to the 12th, that's a trillion. And then it goes on. So by the time we get to radio waves, FM radio frequencies are in the megahertz, so that's millions of hertz, 10 to the 6th. AM radio is kilohertz in the 10 to the 3rd range. So let's do a comparison of numbers. So which would you prefer? And my assumption here is that you would prefer the greater amount of money, $700 or $2 million. And I put in bold print the 7 versus the 2. And if you think about it, the 7 and the 2, you might be wondering, why did he want to emphasize the 7 and the 2? I hope you can see we are comparing hundreds of dollars with millions of dollars. So as you compare hundreds of dollars with millions of dollars, the 7 and the 2 become irrelevant. I would rather have millions of dollars than hundreds of dollars, and I don't really care whether it's 2 or 7. And what I'm getting at here is when we're comparing two quantities, we want to focus on the order of magnitude. The millions are more than the hundreds. So 2 million is 2 times 10 to the sixth. 700 is 7 times 10 to the second. And this is it written in scientific notation, and it helps you better to see the order of magnitude. The 10 to the sixth is greater than the 10 to the second, and the 2 and the 7 become less relevant. So which is larger, 7.7 times 10 to the first kilometers or 1.4 times 10 to the sixth kilometers? And I want your eyes just to go past the 7.7 and the 1.4. Don't even think about them. What we want to compare is the order of magnitude. What exponent is on the 10? Here, you're looking at something that is in the realm of tens of kilometers on the left. On the right, you're looking at something that is in the realm of millions of kilometers. And in fact, 7.7 times 10 to the first, well, that is 77 kilometers. That is about the distance from Porterville to Bakersfield, as you can see on the map right here. 1.4 times 10 to the sixth kilometers is the diameter of the sun, so definitely much larger than anything that would be on planet Earth. This is the end of the part 3 video for chapter 5. Next, I want you to watch the video that I have linked in Canvas, Powers of 10. So in this Powers of 10 video, the narrator is going to start on planet Earth, and we're going to zoom out past the planets and the star systems and the galaxies, and then zoom back in and look at the molecular and atomic structure of matter. And so please watch that video next. That's the end of part 3, scientific notation. Have a great day.